In this course, we will explain some interesting ideas to build models that reproduce a physical or engineering reality with the purpose of solving particular problems. The central idea is to avoid the use of arbitrary hypotheses, which are often used to simplify and facilitate the mathematical treatment of problems. For example, supposing that a certain function is polynomial, trigonometric, parabolic, hyperbolic, etc., implies arbitrariness that possibly will not correspond to the conditions to the problem under study. Therefore, we try to analyze the problem to be solved and to discover the properties that it must satisfy. By imposing them mathematically, I mean these properties, we state differential, functional, or algebraic equations which will lead us to the only functions that are compatible with them. Therefore, we say that we use non-arbitrary hypotheses. In this way, the resulting model will reproduce the reality being analyzed, from which we can discover other derived properties as a consequence of this. We invite you to join us in this exciting task that almost certainly will surprise you. You will enjoy the new ideas proposed in this course, and we also hope this will suggest you other ideas that improve those here and to discover new models to solve the problems that arise every day in your field of specialty. During my long experience in refereeing papers, I have found many examples of incorrect models that become published in prestigious journals if nobody corrects them before publication and are used without any criticism. The consequences of using such models are unpredictable, because they can cause important errors and damages. A contribution to avoid this problem is one of the main motivations to publish this course. A second motivation is the idea of using the least possible number of arbitrary assumptions in modeling, and this is a new one. And finally, a third motivation is to extend the use of functional equations, a tool not inferior to differential equations that supplies relevant possibilities to solve this problem. In the course, I give you some examples. For example, the first one is the use of an inadequate formula. Some authors suggest to evaluate gas emissions by the formula E equal to C1 plus C2AV, where C1 and C2 are constants. E is the emission in grams per second, and A and V are acceleration and speed respectively. If you perform dimensional analysis, you find that the Formula 1 has problems. First, it shows that C1 and C2 have dimensions, but they are not indicated, and then the formula cannot be used. The formula ignores relevant variables with the mass dimension, so that the authors need to include constants with dimensions. Then you can see that identification of valid and invalid formulas must be done with care. The second example is the use of an inadequate parametric family of distributions. To predict the 0.98 percentile of the temperature at a given location based on a sample, somebody can assume that temperatures are log normal. And then you take logarithm, we obtain the mean and the standard deviation, and then we use the formula for the percentile, and finally you recover the original population by using the inverse of the logarithmic function, which is the exponential one. The problem is that if a person in the United States uses Fahrenheit temperatures, the result is 105 degrees Fahrenheit, while a person in France obtains a percentile of 111.3 Fahrenheit, which is not only different from the previous one, but far from it. This occurs because the log normal family is not stable with respect to changes in location. That is, if the temperatures in Fahrenheit degrees are log normal, temperatures in Celsius cannot be normal. Thus, knowledge of what families of parametric distribution can and cannot be used has a high relevance in statistical modeling. The third example is an inadequate use of the domain of attraction for extremes. Consider an engineering design problem in which large winds play a decisive role. Then, it is extremely important to identify the distribution of largest winds. To this end, deciding among reverse Weibull, Gumbel, or Frechet is crucial. Thus, knowledge of the fact that finite or bounded variables cannot have a maximal domain of attraction of Frechet type is relevant. Selecting Frechet as the design distribution is an error and implies a very conservative position that can lead to unnecessary expenses. Thus, a good knowledge of what families of extreme value distributions can be used in a given case is relevant. The example 4 is a statistically incompatible model. Assume that we want to model the statistical behavior of a random variable xy, and we make the following assumptions. First, the conditional families of x conditional on y are normal. Similarly, the conditional families of y given x are normal too. And finally, that the variance of x given y is linear. In this case, no bivariate distribution satisfies these conditions. Thus, we are in front of an impossible model. Our assumptions are contradictory. So this justifies a general discussion about the conditions that can and cannot be imposed in order to have models compatible with the assumptions. The fifth example is the use of an incorrect extreme value probability paper. Suppose some people ignore that when dealing with extremes, there are two different probability papers, one for maxima, the right tail, and another for minima, the left tail, and that only tail data must be used. Using the inadequate paper can lead to serious errors and inconsistencies. For example, when predicting minimum temperatures, the use of the Gumbel probability paper plot in this figure reveals two errors. First, it is a maximal probability paper used for a minimum problem. And B, the model is fitted to all data when only the left tail data should be used. Contrary, this plot is the adequate one because it is a minimal reverse Gumbel probability paper, and in addition, the reverse Gumbel model has been fitted using only the smallest 40 data that is fitting only the left tail on the data. Look that the large data have not been used for fitting the model. All the above justifies the importance of clarifying the role of probability papers and the differences when they are used, A, to identify families of parametric distributions, or B, in extreme value analysis. The aims of this course are the following. We want to analyze some probability models used to reproduce random variables from the point of view of probability and dimensional consistency and physical validity. The main aims of the course are the following. First, to provide examples of random variables used in civil engineering models and to the corresponding families used to reproduce them. Second, to identify, analyze, and discuss the consistency of the most important models used in civil engineering. Third, to identify dimensional problems of some models and solve them by providing alternatives. Fourth, to clarify how an extreme value analysis has to be performed. Fifth, to discuss what type of multivariate random models are undetermined, overdetermined, or uniquely determined, and suggest ways to avoid the under and or over determination. And finally, to give rules to build models without the reported inconsistencies. In this course, we try to build models without arbitrary assumptions. That is a very important idea. Normally, mathematical models of real-life problems are built using convenient mathematical properties. However, when possible, we should avoid this approach. In this course, we base our models in properties that they are expected to satisfy. We start with the dimensional homogeneity conditions given by zoning. These are very important conditions that the reader should know. Zoning in 2001 indicates that dimensional homogeneity imposes the following constraints on any physical relation or equation. First, both sides of an equation must have the same dimension. We cannot add a length with a stress. That is a very important error. Second, wherever a sum of quantities appears in the right-hand side, all the terms in the sum must have the same dimensions. We cannot add a length with a stress, or a speed with an acceleration. We need to add a speed with speeds, acceleration with acceleration, stresses with stresses. And finally, all arguments of any exponential, logarithmic, trigonometric, or other special function that appear in the equation must be dimensionless. Given the dimension of a physical variable x, the dimensional of x squared, of x to the third power, or even the square root, are known, and they are not the same as those of x. But what are the dimensions of log x, of exponential of x? What is the meaning of log meter, or log Pascal? That has no sense. Note, for example, that the exponential function can be developed in series as 1 plus x squared divided by 2. But look, 1 is dimensionless, has no dimensions. If x has dimensions, it cannot be added with 1. If x has dimensions, x squared has different dimensions than x, so you cannot add x plus x squared. It has no sense. So we need to be careful with that. One of the lessons is dedicated to the Buckingham theorem, which is a very important theorem. In this lesson, we introduce the Buckingham theorem, which we should use always as the first step in building models for a physical or engineering problems. These theorems permit us reducing the number of variables in a given problem because the initial variables can be replaced by dimensional ratios, and the number is reduced. If all the arguments are dimensionless, any function relating them is compatible, and then we don't need to worry any further. Contrary, if the variables have dimension, we must be careful of not violating the zoning dimensional rules already commented in this course. Next, we explain how a model should be constructed to reproduce physical or engineering problems. This is not a trivial problem, and the existing literature is full of models which do not satisfy the minimum requirements to be valid physical or engineering models. The models presented in this course are written in terms of dimensionless variables. Models whose variables have dimensions can be wrong or not, and not the simplest models. To this end, the Buckingham theorem is an essential tool which should be used when building models. Buckingham pi theorem states that if we have a physical equation involving n variables, and these are expressible in terms of k-independent fundamental physical quantities, then the original expression is equivalent to an equation involving only n minus k dimensionless variables, constructed from the original ones. Ignoring dimensional analysis is an important error that can lead to more complex models and or to invalid models. Frequently, we find models whose parameters dimensions cannot be determined before other parameters are known, and the Buckingham theorem avoids these errors. So the Buckingham pi theorem tells us three things. First, whether an initial relation of variables is valid for a physical relation among them. Second, the minimum number of dimensionless variables, the pi variables, needed for a given relation. And third, what set of dimensionless variables can be used. The final conclusion is that modeling must always start with the Buckingham theorem with two aims. First, to reduce the dimensionality, and second, to obtain dimensionless variables. We must be aware that there are many options for selecting the dimensionless variables. Any minimal subset of variables associated with a full rank leads to a possible set of dimensionless ratios. In some cases, we could postpone this decision in our modeling process. Before selecting a model, I want to explain an example of a fatigue model. So before selecting a model for the fatigue problem, we need to identify the variables involved in the problem. For example, assume that from previous experience accumulated in the study of the fatigue phenomenon, we know that the variables which are relevant to the fatigue problem are the following 12 which are described in this transparency. You can take a look and see what the variables are. Next, once we have identified these variables, we need to perform a dimensional analysis by means of this dimension table. We need to write each variable in terms of basic magnitude, such as mass, length, or time, and using the exponents. And from this table, we select any minimal set of basic variables leading to a full rank of this matrix. So we need to find the rank of this matrix that gives you the number of variables that will be reduced from the model. In this case, you have one, for example, which is N0, delta sigma 0, and L0, from which we can build the dimensional ratios. In this case, we have 9 dimensional ratios, which are indicated by asterisks, and the meaning of each one is given in the table. And they are constructed from the variable and from the reference sets, in this case N0, delta sigma 0, and L0. This means that any valid physical relation involving the initial 12 variables and without loss of generality is of the 4 given there, where eta is a function of the 9 dimensionless variables. In the course, we describe the Sonic ball example, which is a very interesting one, and will facilitate the understanding of the Buckingham theorem. We also study the simply supported beam example, in which we consider these 12 variables that you have in this transparency. And here I want to show you a counterexample of the well-known Paris law. The well-known Paris law is given in the expression at the top that gives you how the crack size grows, the speed of the crack grow, and is equal to a constant c times delta k, which is the stress intensity factor raised to the m power. This formula has many problems. First, the variables a, n, and delta k are not sufficient for a physical relation to be possible, because the rank is 3 and n minus k is equal to 0. Since the derivative of a with respect to n and delta k have different dimensions, c must have dimensions. It cannot be dimensionless. And then the problem is that we cannot know the dimension of c until we don't know the value of m, and that is a serious problem. And even for different materials or for different loads, the dimensions of the constant c may become different, and this has no sense. But unfortunately, most modified versions of this law have dimensions problems too. Here, I give you one example of a crack growth curve that satisfies all the conditions. You can see the dimensional analysis in the top part in the table, and you can see what the dimensional ratios are, and finally you can see the formula which satisfies everything because we work with dimensionless variables. And finally, we end the course with the example of a general turbulent evaporation formula that is given by Kalisch, was given by Kalisch in 1990. You will see the details in the course. The next lesson is dedicated to model similarities. In this lesson, we define the concept of complete and incomplete cell similarity, which are important concepts when using the Buckingham theorem to derive physically and dimensionally valid formulas. When the incomplete and cell similarity assumptions hold, we can simplify our models a lot. Thus, it is important to identify the practical cases in which they really hold. In the course, we define the concept of complete and incomplete cell similarity. For example, the definition of complete cell similarity means that one of the pi dimensional ratio can be removed. That is that dimensional ratio does not play any role, and then we can remove it. This means that we can simplify even one variable more. And the incomplete cell similarity concept means that we can extract one of these dimensionless ratio outside of the formula and using an exponent gamma. So we don't need to determine the phi function for all the remaining ratios, because one is out of that, and that simplifies a lot the problem. In here, we apply this concept to the case of the modified Paris formula. This is the formula that has no dimensional problems. This is the dimensional analysis with the table that is in the center of the transparency, and that leads that that we have only four dimensional ratios, and then we can obtain 1/c dA with respect to dn as a function of the other three. However, if we suppose that the incomplete cell similarity for delta k divided by delta k th holds, we can simplify the expression as is indicated in the center formula, and even assuming also complete cell similarity with respect to kfc and delta k th and r, we get the formula on the lower part, which is a different formula, but very similar to Paris law, but this has no inconveniences of problem of inconsistencies. The next lesson is dedicated to physical model consistency, and we define this concept. The idea is that if we have a formula of one variable xn plus 1 as u of x1, x2, xn, then we can define this condition. The general non-constant and continuous at a point expressions of real value scale variables in terms of independent scale variables, it is the general solution of that functional equation is the one given in the lower part. This means that when you change the scale in the variables x1, x2, xn with coefficients of factors r1 to rn, as is indicated in the left-hand side, we must obtain the previous formula, the u of x1, x2, xn, but affected by a change of scale of that variable. But that change of scale factor should be a function of the change of scale factors that we have used in the other side. If you have some time, you can try to understand what this equation means, and you will see that it is very reasonable to force for this condition. It is interesting to see that some well-known physical formulas are of this form. For example, the classical formula for determining the bending stress in a beam, or the hydrostatic pressure, or the Ohm's law, the ideal Gauss law, or the Newton law of universal gravitation. The formulas in the right-hand side, you can see products of variables raised to powers, in this case raised to power 1, and in the denominators you can see exponents which are 1 or 2, as in the case of the universal gravitation. So this means that all these formulas are of the same form, products of variables raised to constants, to constant. And this can appear in the numerator or in the denominator depending on if they are positive or negative. This is not a coincidence. This is the result of the condition that we have imposed in the functional equations before. The next lesson is dedicated to probability consistent models, and in this lesson we deal with models such that the probability and statistical assumptions do not contradict themselves and with other assumptions. More precisely, a model is said to be probability consistent if they are not contradictions among all its assumptions from a probability point of view. We discuss this consistency problem in more detail in the course. You have some examples, for example, the traffic, and we have also the definition of a stable parametric family. You can see the details in the course. An interesting case is the case of reproductive families. They are models that satisfy the reproductive property that is crucial in a stochastic model in which variables are sums of other variables, and this imposes some constraints on the associated distribution function. In particular, the definition of reproductivity is the following. We say that a family of random variables is reproductive if the sum of two independent members of the family belong to the family. That is, if it is closed or stable under the sum of independent variables. The practical relevance of reproductivity is that adding independent random variables from a given family will remain in the same family of distribution, that is the summands and the sum shared distribution family. The key tool to work with reproductive families and derive their properties is the characteristic function. We give in the course several examples of reproductive families as the binomial family, the normal family, the negative binomial, and it is interesting that you learn that because in your models you can use these reproductive families to simplify things a lot. So I invite you to follow this course to learn these things. The next lesson is dedicated to extreme value consistent models. In this model, we consider the case of maximum and minimum of independent random variables that is given by this theorem that appears in the transparency. If I from 1 to n are independent random variables with common cumulative distribution function f, then the cumulative distribution of the maximum is the same raised to the n power, and the cumulative distribution of the minimum is the expression that you have there. This theorem permits us to analyze string operations stability. The Weibull, reverse Gumbel, and reverse Frechet distributions are stable with respect to minimum operation, that is, the minimum of a finite set of independent random variables in any of these families belongs also to the same family. And the reverse Weibull, Gumbel, and Frechet distribution are stable with respect to maximum operations. In this figure, you have a plot in which you can see that Weibull, Gumbel, and Frechet distributions are ordered in terms of severity in this order, as in the figure, where the Gumbel distribution separates the Weibull and Frechet families. Weibull and reverse Weibull are not compatible with a bounded lower and upper end respectively, and Frechet and reverse Frechet are incompatible with bounded ends respectively. A common error is to select a Frechet distribution for a limited random variable or a Weibull distribution for an unlimited one. This must be taken into account to avoid important errors. An important problem is to know which distribution should be used for extremes when you know the parent cumulative distribution function. There is a theorem by Castillo et al. That gives you a very simple way of deciding this convenient distribution. You just need to take the limit of this expression, and depending on the value of k you obtain, you can see if it is a Frechet type, a Gumbel type, or a Weibull type. In the case of maxima, you need to replace that expression for the one in the lower part of the transparency, so you can solve the problem for maxima. In the course, you will be given important tables with the distributions to be used for minimal and maximal problems of the most well-known distribution: normal, exponential, or normal, gamma, Weibull, Frechet, any one. And that is a very interesting information that can be useful to your models. Another important problem is what happens if you don't know the parent distribution? What happens if you only have a sample? If you have only have a sample, you can use probability papers. It is important to know that there are two types of probability paper, one for minima and one for maxima. The one above is for maxima and the one below is for minima. You need to plot the sample only in the yellow area. For maxima, you need to plot the largest value, for minima, the smallest values. And then, if you get a linear trend, the distribution to be used for extreme is Gumbel. If you get an asymptote, vertical asymptote, the distribution to be used is Weibull. And if you have the other curvature, you need to use the Frechet one. So this is a very simple way to determine which distribution should be used when you have only a sample. We can use the formulas, or you can use the probability papers. But in general, I recommend you to use the following rules. First, if the random variable is bounded in the tail of interest, eliminate the Frechet domain of attraction, and otherwise eliminate the Weibull domain of attraction. If the data is maxima, plot the data on the maximal Gumbel probability paper. If it is minima, on the minimal Gumbel probability paper. If the tail of interest, the right for maxima and the left for minima, shows a linear trend, the domain of attraction is the maximal Gumbel family and the same minimal for the other probability paper. If the tail of interest has a vertical asymptote, then the domain of attraction is of the Weibull tab. Otherwise, the domain of attraction is the Frechet one. In case of doubt between Gumbel and Weibull, choose Weibull model. In case of doubt between Gumbel and Frechet, choose Frechet. And these rules will facilitate you a lot the work to be done. So I invite you to follow this lesson carefully to have a better knowledge of extreme values and to avoid serious errors. Normally, a single pass of the video will not be sufficient to be familiar with this important concept, so go several times to have a better understanding of the problem. The next lesson is dedicated to dimensional analysis of distributions. In this lesson, we analyze different families of distribution from the point of view of dimensional analysis. We will see that some families are not appropriate in certain cases, and knowledge of cases where these problems arise will avoid us the use of incorrect models. For example, we need to take into account the dimensions of the mean and the variance in the different families. For example, the mean and the variance of the Poisson distribution are lambda and lambda, are the same. This means that this family is only valid for dimensionless variables, because the dimensions, if the variable has dimensions, the expected value will have the same dimensions of the variable, but the variance will have the square of those, and they cannot be identical. So this variable is only valid for dimensionless variables. The same can be said for the binomial family, because the expected value is np and the variance is np1 minus p. You can see that p must be dimensionless because it appears 1 minus p. If 1 is dimensionless, p has to be dimensionless. We cannot subtract variables with different dimensions. So p is dimensionless. And then the dimensions of the expected value and the variance are the dimensions of n. So n has to be dimensionless and the variable has to be dimensionless to be valid the binomial variables. The uniparametric exponential family is compatible because the expected value is 1 over lambda and the variance is 1 over lambda squared, so the dimensions are the squares of the other one. For example, in the gamma family, we have no problem because theta is dimensionless, but lambda no, is not dimensionless, but the expected value is theta over lambda, and the variance is theta divided by lambda squared. That means you have lambda and lambda squared, and it should be to have no problems with dimension, variables with dimension. In the case of the negative binomial variables, we have problems too, and you can see that the dimensions of the variables should be r, and the dimension of or the mean and the variance is also r, and that cannot be possible if the variable has dimensions. Finally, we have the log normal family that gives you the expectation and the variance that are not compatible, so you have problems with this random variable if you use it for variables with dimensions. Finally, the chi-square also has problems because it is not location stable, and then has problem if you use it for variables with variables that have dimensions. Fortunately, neither the normal nor the extreme values have dimensional problems. In summary, we are led to the conclusion that working with dimensionless variables is dimensionally safe, while otherwise dimensional problems can occur, and then the Buckingham-P theorem plays a fundamental role. We study in the course also the mixture of distributions, and we give some interesting examples, as the mixture of a binomial with a Poisson, the mixture of a binomial with another binomial, the mixture of a multinomial with a Poisson, or the mixture of a gamma with a Poisson family. We also explain the relevance of the central limit theorem that tells us that if we sum a sufficient number of variables, we have an approximately normal random variable, and we can use this property in our modeling problems. We also discuss infinitely divisible distributions, which are also very useful and an alternative to normal models. The next lesson is dedicated to multivariate models. We define a multivariate model. To define it, we need to provide the joint probability or density function of all variables in the model, and this can be done in several forms, but some of them can lead to consistency problems. So knowledge of these problems and how to deal with them is of crucial importance to avoid invalid or non-existent models. In the course, we dedicate some time to multivariate underdetermined models, that is, conditions that don't determine sufficiently a unique model. This can be done by means of parametric marginals, or can be done by means of regression functions, by means of first and second conditional moments, by means of conditional in location families and given regression with constant variances, and by means of conditionals in scale families and given regressions, and by means of location scale families with specified moments. We need to say that you should be very careful, because in most of the cases you don't get a unique solution, and in other cases you can have some problems. We also dedicate some time to define a multivariate model uniquely. This can be done by means of a multivariate parametric family. Of course, this parametric family has been studied and they are consistent, so we have no problem if we use this alternative. We can define by means of set of marginals and assuming independence, but unfortunately this only leads to independent case. Or we can use by means of conditionals and marginals in location scale families and non-constant linear unboosted-adjusted regressions. And then we need to solve a functional equation that explains us what are the possible solutions. We can also define the model by means of one conditional distribution and the other regression, and then we will describe in which case you have a unique density. And finally, the most important of all the methods are Bayesian networks. Bayesian networks models are useful to reproduce multidimensional families of distribution by defining a special subset of conditionals to avoid incompatibility. A Bayesian network is a pair, G and P, where G is a directed acyclic graph on the set X of variables, and P is a set of conditional probability densities, one for each variable, and pi sub I is the set of parents of node xi in G. The joint probability density is simply obtained by the product of all these conditional probabilities. And the graph G contains all the qualitative information about the variables, and P contains the quantitative information. So together we'll give you the model. In a Bayesian network, we include only the parents of each node. That is, we simplify substantially the joint density. We point out that we can define independently each of the conditionals. So it is very easy to do it, because we define the joint density locally, only defining the conditional densities of each node given its parents. And then we write the joint density, as you can see in the expression, by the product of all these conditionals. As explained in previous sections, defining models by their conditionals and or imposing given regressions can lead to incompatible models. The main advantage of defining multivariate distribution as in four, that is, by Bayesian networks, is that they are always compatible if we guarantee that each factor is a valid univariate family of densities. This is very relevant in practice. In the course, we present an interesting example given by Castillo et al. In 1997 to study the damage of reinforced concrete structures. and based on damage or a damage indicator variable. You can see that we have a directed acyclic graph that is given in this figure, very simple, and we can obtain, as soon as we know some more data, how the damage level is. At the beginning, we have a very wide density, so it is not clear what is the quality of the structure. When we increase the knowledge in the step 5 or 5th or the 11th, 12th, even in the 16th, you can see that you have a density which is very precise, so that tells us that the quality level is 12, that is large enough for avoiding any action. Castillo et al. Also provide a very interesting Bayesian network to analyze the safety in highways. The idea is to reproduce the highway with all the elements and to build a Bayesian network including all the variables having influence in each of them, and then joining them together to build the whole Bayesian network. You can see the directed acyclic graph in the A picture on the top. The B picture is just a scheme of the road. The C gives the kilometers or the points where the different elements appear. And finally, the D plot gives you an idea of the risk or the probability of failure or accident that you have at the different points, so that you can order the different points by risk. And finally, here you have the road. An example in the left, you can see the red line, which is the highway. You have in the figure the location marked in blue color, the orthophoto of the given location and surrounding area, and the risks associated to that area, so that you can immediately obtain the risk you have at any given point in the road and measure by using Bayesian networks what are the risks. And finally, we analyze a fatigue model in a lesson dedicated only to this. In this lesson, we derived a model for the SN fatigue curves. The idea is to base the model on the properties that it should have and avoid arbitrary assumptions. We must observe that how the fatigue process behaves to find some properties expressible in terms of mathematical or statistical equation, so that solving these equations we can obtain the families of SN curves that satisfy the corresponding properties, at only those. This, apart from avoiding arbitrary assumption, permits rejecting any of their families as invalid ones. We explain the process to derive the fatigue model, but first we include the stress range and later the stress level to finally obtain our model. In this model, we can use the results that we obtained previously in the course. You remember we have 12 initial variables for the fatigue problem that can be reduced to 9, but here, because we are studying only the SN curves, 4 more can be eliminated, and then the problem depends only on 5 variables, which are the N, delta sigma, sigma L, L, and P. So we, according to the Buckingham theorem, we have a relation between these 5 variables. Next, we use a compatibility condition, a consistency condition that reflects independence with respect to units of measure, and a statistical string condition. With these conditions, we are going to derive the only model that satisfies them. And we look for a relation of the form given in the lower part, that is, we want the probability of failure at, after n cycles when you subject the specimen to a stress range of delta sigma and a stress level sigma L when the specimen length is L. Here you can see what happens if you test at a given delta sigma, and then we get the failure of the specimen at n. Unfortunately, because it is a test in which we destroy the specimen, we cannot repeat it, but we know that if we could be able to repeat the test for different delta sigma, we will get different values which are indicated in this blue line. Since the specimen is random, we can get different lines, not only one. And then we can consider the random variable delta sigma given n or the random variable n given delta sigma, these two conditional, but observing that the number of lines that pass through the shadow areas should be the same. If one line passes by the first shadow, it should continue and it necessarily has to pass through the other line. Those areas should be the same. To discover that these areas should be the same, this is a very strong condition that can be imposed in our functional equations. And then we impose these conditions and we get the consistent conditions for this case, and we get finally a functional equation which is given in the upper part of the transparency, which is a functional equation because it is an equality and has 4 unknown functions, mu1, mu2, sigma 1 and sigma 2. Functional equations are able to solve with only one equation the form of the 4 equations. And then with this we get 2 possible models. The model 1 and model 2 in the transparency. The model 1 gives a curve curves that are hyperbolas, and the second gives parallel straight lines. So it is interesting to see that only using these properties we find the hyperbola or the straight line as the only possible curves, and all other are not valid. Using asymptotic properties for the weakest link principle, we can find that the model should be Weibull or Gumbel, and then we have these 2 models for the percentiles. In summary, the compatibility condition and the weakest link principle and statistical and physical considerations allow us to obtain the functional form of the SNM models above. This is for a test in which the minimum stress has been fixed and we have changed only the maximum sigma. You can see these 3 cases in which the sigma min, sigma m, lowercase m is the same, but the values of sigma capital M are different. And then we get this curve. But this model is also valid if we fix the sigma m, capital M, and vary the other one in blue color. So we can have 2 models, but these 2 models has to be compatible because the intersection of those models belongs to both. And this is a very strong condition that allows us this condition that you have here. We have in red color and in blue color the cases depending of which of the extreme stresses are fixed, the maximum or the minimum, but they should intersect as horizontal lines. The condition of this family of curves to intersect as horizontal lines is very strong and give us a functional equation that is the one that you have here in the center of the transparency. This functional equation in green color is a functional equation because it is an equation and it has 8 different unknown functions, those with lowercase and the uppercase m. And it is interesting to see that with functional equation we can solve this functional equation, and if we solve the functional equation we find our model, which is this one, the model innate, where the meaning of the R and S functions are given in 9 and 10. So it is very interesting to see that this is a model in which there are no arbitrary assumptions, and this solution is resulting from the properties that we have forced. If we include, as before, the weakest link principle and the extreme value theory, we get these models. The next lesson deals with Kraft-Grow model, and we are going to develop a Kraft-Grow model. The process, as in the previous example, consists in identifying some properties the model must have and use them to write the corresponding functional equations. And the solution of this equation, which is not always easy, gives the only possible solution. We will also show an example from the literature that shows how to solve observed model inconsistencies by correcting commonly used models. Crack-Growth curves represent how the crack size increases as a function of the number of cycles under constant stress range delta sigma and stress level sigma L. These curves are used to derive the crack growth rate curves to be applied in the fracture mechanics approach. Next, several crack growth models are derived. As usual, we start from observing crack growth experimental results, and we try to use no arbitrary assumptions or lightly restrictive assumptions. A typical example of crack growth curves for three different combinations of constant stress ranges and levels is shown in the figure, in this figure. Note that because the model is random, we don't get a single curve. We have written 3 percentiles for different 3 load conditions. The one on the left corresponds to a very strong load. The one on the right corresponds to the lightest strength condition. And then what we need to do is to observe these curves that have been obtained in the laboratory and see what properties they have. And we do that carefully. And then what we look for is for a function that gives you the crack size A when you start from a crack size H0 and we apply n cycles and a load condition Q. But this has to satisfy a very important consistency property. The formula must provide the same result if we load first for n1 cycles and then we load for n2 extra cycles, that if we directly load for n1 plus n2 cycles. Since both values must provide the same result, no matter the values of n1 and n2, the following functional equation must be satisfied, that is the one in the lower part of the transparency. You can see there that the first expression it corresponds to starting from an initial crack size A0 and applying N1 plus N2 cycles. In the right-hand side, you see that first we calculate the crack size when we start from A0 and apply N1 cycles, and once we know that crack size as the initial for the second step, we applied N2 cycles, and then both must be equal. But this is a functional equation because it is an equation and the unknown is H asterisk. So we have to solve that functional equation. In this case, fortunately, this is a very well-known functional equation, which is the translation equation, and we know the solution. The solution is given by that, where phi is an arbitrary invertible function with respect to the first argument. This beautiful result, which is of great interest from a practical point of view, states that one cannot choose an arbitrary function of 3 arguments, H asterisk, to represent the crack growth problem, and that the only degree of freedom consists of a 2-argument function phi invertible with respect to the first argument. So this simplifies the problem a lot. It is interesting to see that Melby and Kobayashi in one paper use a damage curve which is the one on top of the transparency, and they reveal that they have some problems because they get different results if they use the formula in 2 different ways. And then they decide to change the formula by the second one, which is the one on the lower part. And then they say that this solves completely the problem. The problem is that the equation 14 is invariant with respect to time origin changes, but 13 is not. That is, damage produced depends only on the previous damage, but not on how it has been reached, lack of memory. And then we can check that the Melby and Kobayashi example doesn't satisfy, in equation 13, doesn't satisfy the condition, because if we apply N1 plus A2 at once, we get one result, and if we apply first N1 and then N2, we get a different result. But with on the contrary, with the formula 14, we get exactly the same result as you can see in the transparency. So this explains the use of these models. From this model, we can see a beautiful result is that the densities are simply translations of one to when the crack size increases, but changes with the applied load. And this is very interesting result that come from this. Another possible compatibility condition that you can imply is similar to the one from the SN curve, when we can assume that we can repeat the process of increasing the crack size for different loads and different specimens, and we can see that the number of specimens going through the two shadows area should be the same, and then we get the functional equation that we have in the transparency. That can be written in this form, that is equation 16, when we solve it. And then we have, of course, two models, model 1 and model 2, for the crack size growth curves. And you get, again, hyperbolas and straight lines as the only possible lines that satisfy this condition. So this is an extremely interesting result, because we know that all other lines do not satisfy this condition. Doing the same, that is using extreme value consideration and the weakest link principle, we can get the final model, which is the one you have there, and also this other model. And finally, we can write the crack growth percentile curves that are in the lower part of the figure. Another interesting compatibility condition is to force the same densities for the same damage, even though we use different load conditions. You can see there that you have three load conditions, Q1, Q, and Q2. But you can see that the densities, when you have the same crack size, are the same. So this is the condition we imply. And this leads to a functional equation, which is the one in the center of the transparency, that can be solved, and then you get the only model that satisfies this, that is the one you have there. This is a very nice result. And I invite you to follow this lesson several times, because it is difficult to follow, but I think the ideas in the lesson are very interesting, of practical relevance. And finally, we study the compatibility of the SN and the crack growth models. In this lesson, we connect the SN fatigue and the crack growth models. Traditionally, these two problems have been treated separately, when in fact they are closely related. In this lesson, we describe how we can move from one model to the other and vice versa by simply adding the failure curve. This is the key picture of this lesson. In the upper part, you have our model for the SN curves. In the lower part, you have our model for the crack growth curves. And in the lower plot, you have on the top blue line, which is the failure curve. And you can see that moving from one model to can get the other, and vice versa. And that is because we force the compatibility. If we force the compatibility for all percentiles, we just need to take the percentiles of one of the models, the percentiles of one of the other, and make it both equal. That is what we do there. And then we get a functional equations that can be solved to get the final solution. And that is the way of obtaining the solution that we've had on. In the course, you can see the details of all this. And this is the end of this course. You will see that the SN and crack growth models are closely related, and that we were able to build models that consistently reproduce this relation. I hope this course to have opened your mind to the relevance and consistent and arbitrary assumption as two key ideas for building physical and engineering models. We have the following conclusions derived from this course. First, working with dimensionless variables is mandatory to avoid important errors. Second, the Buckingham theorem solves the dimensionless problem and reduces the number of variables in the model without loss of generality. Contrary to models built based on mathematical convenience assumptions, they should be constructed based on physical, engineering, or mathematical properties that the model is expected to satisfy. And finally, the properties must be stated as functional differential algebraic of other equations which when solved provide the unique valid forms of the model functions.